Should I get started now? Okay. Okay. Hello, I am Adam. By the way, guys, I'm going to get started right at 7, so just to give people some time. I'm going to run to the bathroom for one moment. I'll be back. All right, guys, I'm going to get started. Hello, my name is Adam, if you've never met me before. I'm one of the SARC tutors, and today I'll be holding a study union review for Physics 1 for engineers. If you're in Physics 2053, the college physics, you're welcome also. It's kind of like the same material, basically. So I've got 17 questions lined up. So I'll just be going through them one by one. I got these practice problems from other sources. I didn't really write all of them necessarily. But I'm going to say this right now, and I'll say it at the end. The best way to do well in this final exam is practice problems. That is number one. That is always number one. I can't teach you that much. I can try and impart my wisdom of how to approach problems, but it's all going to come down to how many problems you guys do. Okay? So let's get started with number one. Okay. This is my first time using a document camera, so I'm sorry if I'm not good at it. Okay, so for this problem, a double-decker bus is traveling at 10 meters per second. A child in the bus throws a ball horizontally out of the window from a height of 5 meters above ground level, with a velocity of 5 meters per second in the direction perpendicular to the side of the bus. With what speed does the ball hit the ground measured relative to the ground in meters per second? Okay, so this is kind of a confusing problem, but the first rule is to always draw a little diagram, okay? So I'm going to draw a bus. And by the way, my drawings are going to be really horrific the whole time, so. All right, so that's our bus. It's traveling, let's just say this way. Okay, it's going at 10 meters per second. So a child in the bus throws a ball horizontally out of the window 5 meters above the ground. Okay, so let's just say that person they're right there. And that's 5 meters above the ground. Oh, I'm drawing way too small. I'm sorry, guys. Okay, so I'm going to draw this a little bit bigger. We've got, yes?
Is every exam for physics going to be covering the last 3 chapters, or are like some of them going to be cumulative and some of them going to be, because ours is only the last 3 chapters of physics.
It's mostly chapter 8 and 10.
So my review is cumulative.
Okay.
Yeah.
This isn't our next exam.
Okay.
I'm sorry if it doesn't totally translate to your material. I don't know how much of chapter 8 or 10 I have in here. I'm just going to warn you. So if you want to leave, just.
Okay. Thank you.
You're welcome.
Like this and stuff.
Okay, so at a height of 5 meters, so there's this ball, and it's going this direction at 5 meters per second. And it's going to have some trajectory, like and it'll hit the ground right here. All right, so my rule of thumb, after drawing a little diagram, if it's not already provided, is to write down everything you know. Write down every single thing that they give you, whether it's important, whether it's not, you'll find out later. And that especially goes for kinematics problems, because it makes it a little bit easier to visualize. So I'm going to split it up into x and y components. So let's see, what do we have? We have the velocity in the x direction for the ball. Time we don't have, but that would probably be useful. And most of our stuff is in the y direction. So what do we have? We have a change in the y, or height, of 5 meters. We have a acceleration, which is always g for the most part in these kind of problems, which is negative 9.8 meters per second squared. That's kind of most of what we have right now, okay? So one kinematics equation that we can use to get a final velocity is given by this equation. And I just have this off the top of my head, but you guys will have all of these on your formula sheets. So you can just, when you write this stuff down, you can then look at your formula sheet and go either through x's or y's and then get the components from there. So this is one equation that is on there. Okay, something like this. They might use h instead of delta y, but it's all the same. So there's one thing that I didn't write down that I should have. What is the initial velocity in the y direction for this ball?
0.
It's 0. Okay. So back to this equation. We know that's 0. So plugging in VFY will be the square root of 2 times negative 9.8 meters per second squared times, what am I doing? 5 meters. Okay. And then when you do that math, because that's just normal math, you'll get 9.9 meters per second. Okay. Now let's keep in mind the direction that this is going in. Because the velocity of this ball is going downward, we need to consider that a negative 9.9 meters per second. And now that I've gotten this, I'm going to put it back in my little knowns area. So what are we really looking for here? We're looking for what speed does the ball hit the ground in meters per second. It says nothing about what direction necessarily. It's not the direction in the speed in the y direction, the speed in the x direction. So what this is telling you is it's an overall speed that you need to be getting. Okay? So generally for vectors and stuff, we have something like right? So your velocities will just be the square root of all the squares added together of the velocity in the x, the y, and the z. A lot of the times you guys won't have z velocities, but in this one you actually do. Yes?
In the y component equation, why is the delta y not negative?
Why is delta y about what?
Not negative?
That's a good question. So it kind of depends on how you want to think about it. We could have made that negative, and that would have just given us, well, then that would just give us a square root of a negative number, so then that would have kind of come out weird. Yeah, that actually probably should have been negative. That should have been negative, but if you can just keep track of what should be positive and negative in your head based on the drawing, then you should be okay anyway. But that should have been negative. So this velocity will be the addition of all these other velocities squared. So we already have Vx is known, Vy is known. Do we have a Vz? That is a good question. Yes, we do. So let's go back to our main bus picture right here. So the bus is moving in the x direction, or what I'm calling the x direction. The ball is thrown, I can't really describe it, but it's kind of going into it's coming out of the page, right? The ball is being thrown out the side of the bus. So let's call that our z direction. And that's represented by that dot. And then the y is how the ball kind of sputters to the ground over here. Okay? So that's our velocity in the y. So we're going to call this 10 meters per second. That is Vz. So to get our overall velocity is the square root of Vx, which is 5 meters per second, squared, plus Vy, negative 9.9 meters per second, squared, plus the Vz, that 10 meters per second, there. Okay. So when you add all those up and do the math, you get an answer of V is 14.9 meters per second. So this is kind of a weird problem, and it's a tricky problem, but it's a good way to keep in mind all the different directions you have, because I know your professors made vectors a really big point, and the reason they did was for situations like this. They don't really care that you can do the dot product. They care that you can apply the dot product or apply vector magnitudes and stuff like that in problems like this. So it's kind of a messy problem, but here it is. And I'm also going to be posting what I write down on these pieces of paper on the Study Union website. So keep that in mind. So let's move to number 2. So we have 2 equal masses on opposite ends of a 10-meter long massless string. And the string is hung over a massless, frictionless pulley, which is 8 meters above the ground. Initially, one mass is 5 meters above the ground and moving downwards with a speed of 5 meters per second. How fast is it moving the moment it hits the ground? So I'm going to draw this out. So we've got this massless, frictionless pulley. And on one side, we've got m. And on the other side, you also have m, because they're 2 equal masses, right? Something like that. So the whole string is 10 meters long, and the pulley is 8 meters above the ground. Interesting. Okay. So let's call this 8 meters. Okay. So we have initially one mass is 5 meters above the ground. So let's just say it's this one for right now. Let's call this the ground. So this is 5 meters. All right. So main question, how fast is it moving when it hits the ground? So we're looking for a final velocity, right, of VF. So because this is it's a massless pulley and it's frictionless, and the masses are equal on both of them, we could almost treat this as 2 masses on one pulley, or on just one plane right there. So I'm going to redraw this in a way that might be a little easier to visualize. Okay? So here are the 2 masses of mass m. Based on this drawing over here, what forces do we have acting on the 2 blocks?
Gravity, tension.
Gravity and tension, right? So you've got a tension moving this way for both, and then you have a mg. Right? And that's all that's really acting on it, because there's no friction, there's no other masses, there's nothing. So let's imagine this is the pulley right here. So you have mg pointing in both directions, and then a tension pointing this way. So based on this diagram right here, if you were to do the sum of the forces, what's the sum of the forces going to be? It's going to be 0, because they cancel out. Okay? So we know m has an actual mass, so this means that a must equal 0. What does it mean if acceleration is 0? Acceleration is the change in velocity over time. So if the acceleration is 0, the change in velocity is 0, so the velocity never changes. So because it was at one point moving with a speed of 5 meters per second, right? That means it's also going to end that way. So the initial velocity is 5 meters per second. That means the final velocity is 5 meters per second. And I'll just write out when a equals 0, the change in velocity over the change in time equals 0. All right, so this is our final answer, 5 meters per second. It's kind of another trick question, a weird question, but it's something that a professor could easily ask just to see if you know the concepts or not. Because you're not going to have too much time to finish the exam, so a lot of them will be ones that they expect you to be able to get quickly, like this one. Okay? So does anyone have any questions on this problem? Okay. So I'm going to move to number 3. Okay. So we have a function v of t in the figure. It describes the velocity of an elevator moving up and down in a building. At which labeled point is the elevator at its highest point? Okay? So, let's think about this. For position, how does position relate to velocity?
Position, velocity is the first derivative of position.
Yeah, velocity is the first derivative of position, so it's the change in x over the change in time. So if we're looking for the highest x, okay, for this kind of problem, this one's pretty easy. So if velocity is positive, x is also going to increase. That means the elevator is going up, right? When the velocity is negative, that means the elevator is moving down, right? So based on this graph, from points A to B, because the velocity is positive over this time, let's just put a little plus. From B to C, the velocity is still positive. That means it's still moving upward, right? So we've got a little plus here. C to D. Now, although it's moving down, it's sloping downward on the graph, that doesn't necessarily mean it's not still moving up. It just means it's going at a slower rate. So that kind of means it's slowing down. The acceleration is decreasing. So this is kind of when you're getting to your final destination. It has to slow down a little bit when you're getting to your point. So this is still positive. And now from points D to E, that velocity is now negative. So this point is negative. So from D to E, the elevator is moving down. So at which point is it at its highest? The point that it's going to be at its highest is point D, because the velocity is moving up and up and up throughout these points before it moves down when the velocity is negative. So this is a pretty easy problem that if you guys don't have this kind of understanding down, I would really go back to chapter 1 or 2 whenever they go over this stuff, because it really makes your life easier later on. So that is number 3. And on to number 4, one of the more fun problems. I like the force problems personally. Okay, so you push on an 8 kilogram block in the figure from the left with a force of 20 newtons, as labeled here. What is the magnitude of the horizontal force of the 2 kilogram mass on the 8 kilogram mass? Okay, so if we're imagining this, what is the magnitude of the force of the 2 kilogram mass on the 8 kilogram mass? So there's going to be some kind of force coming from the 2 kilogram block, and it's going to be resisting this 20 newton overall force that's being pushed on it. So also keep in mind all surfaces are frictionless, which makes our lives easier. Okay, so what is Newton's second law?
Force is equal to mass times acceleration.
Force is equal to mass times acceleration. That's right. And you guys should know at this point that you can sum the forces and it'll equal ma, right? So in this case, because there's no friction, we're not going to really have anything pushing against it. So we're going to have the sum of the forces is equal to ma, the acceleration of this whole system moving. And that's going to equal that 20 newton force that we're given. So, and this is based on the whole system, okay? So we're going to treat this as one big block. So this is 8 kilograms, and this is 2 kilograms. Sorry, that's a little small. We're going to treat this as one big block. So we're going to treat this mass right here as a total of 10 kilograms. So now we know the acceleration of this whole system of 2 blocks is going to be 2 meters per second squared. So what we're really looking for is the magnitude of the horizontal force of the 2 kilogram mass on the 8 kilogram mass. So I'm going to draw this 8 kilogram mass. This is going to be our new system, if you will. So here we have 8 kilograms. Now, we know we have a 20 Newton force pressing on it, right? That's based on that initial force from up here. But what we also have, and what the problem is asking about, is what about this small force from the 2 kilogram block onto that 8 kilogram block? When you have Newton's third law, you have a force, you have an equal and opposite reaction. Some poor phrasing, but something like that. So I'm going to call this F. This is the force from the 2 kilogram block on the 8 kilogram block. So now we have a little more of a conventional force analysis. So it's still the same system. They're still tied together. So that sum of the forces equals ma. That acceleration will be the same. They're going to be moving at the exact same rate, okay? Because they're tied together. You're not going to push the 8 kilogram block and the 2 kilogram block goes flying. They're both going to stay together. So that A is related to this A. It's also 2 meters per second squared. So ma is going to be equal to, based on this image right here, 20 newtons going in the positive x direction minus F. Okay? So the mass for this is only the 8 kilograms. That acceleration is the same as before, 2 meters per second squared. And that equals 20 newtons minus F. And then when you solve, you have the force of that 2 kilogram block on the 8 kilogram block. That will be 4 newtons. So this is probably a little simpler than what you guys will see normally, but still a good start to the problems. Does anyone have any questions? Okay. Now we're getting into the weird stuff. The moments of inertia, everyone's favorite. Okay. So we have a solid disk of mass m that's 2 kilograms. So I don't know if it's really going to show up in here. Yeah. So the mass of that disk is 2 kilograms. A radius of 3 centimeters, and rotational inertia given by this equation. It's supported by an axle and has a string wrapped around it. What is the magnitude of the linear acceleration of the string if it is pulled with a force of 10 newtons? Okay, so there's a lot of stuff that they just threw out at us, and it's kind of confusing. I'm even confused. So my number one is to write down everything I know. So what do I know? Okay, I know the mass is 2 kilograms. I know that the radius is 3 centimeters. And just, I like to do this, I'm just going to convert it to meters. There's no point in ever really having it in centimeters. We know that the rotational inertia is given by this equation, which that'll always be given in your exam. What else do we have? Oh, and then we have a force acting on that string of 10 newtons. It's basically being pulled. So we are looking for the magnitude of the linear acceleration of the string. We want to know A. Okay, so let's think about what we know. we can calculate the moment of inertia pretty easily. We can also calculate the torque. So we're given the force acting on this circle times the radius. Okay? So we know torque is a force times a radius. Which equals that 10 newtons that we have times 0.03 meters. That gives us a torque of 0.3 Newton meters. Okay, so I'm going to add that over here to our knowns. Oh, I'm sorry. Now, there's one other equation that we can throw in here. And this is getting into the rotational kinematics. And you guys should also have this on your formula sheets as well. So one thing we also know is that the torque is equal to the moment of inertia times alpha. Alpha is your angular acceleration of the disk. Okay? So we don't really know alpha, do we? But what we do know is this relation. Alpha equals A over R. And this is related to all the others, a few other similar ones. There's going to be omega equals V over R, and theta equals S over R. They're all the same. They're all kind of saying the same thing. Angular acceleration is acceleration over the radius. Angular velocity is the same as equals velocity over the radius. The angle is equal to the circumference of, like, the partial circumference over the radius. So we have tau equals, or the torque equals the moment of inertia times the angular acceleration. So what I'm going to do is I'm going to plug this in over here. So torque equals I times A over R. And this is good because now we have A in our equation and we need that. And that's what we're trying to solve here. So I'm going to rearrange this equation. A equals tau R over I. And we also know an equation for I, 1/2 mr squared. That's given. So tau R over 1/2 mr squared. Okay? Sorry, I can't move. This is my spot.
Just the little part move, maybe? That's weird.
I mean, there's like a lot of chords associated, right? I mean,
Quick question.
yes.
What happened to sine? Because isn't it,
Sine?
because isn't torque equal to the product of like the radius times the force, and then
You mean like the sign is in positive or negative, or like a sine cosine
isn't
sign?
it the cross product?
Yeah.
So that's another way that you could find that.
Okay.
That's not really needed for this problem, but
Would probably be one or.
that's more if you have two vectors is when you'd use the cross product. So your force would be given by some type of like x, y, and z components, and then your radius would be x, y, and z components, and then you'd go from there. Yes.
I'm not sure if it's right, but I think it's 1 in this case because the radius is perpendicular to the force, the directed force, the line of action.
What's 1? What do you mean by that?
Because the sine of 90 is 1. So that's why it's okay to use RF.
Yeah, no, that's a good point. So it's similar to if you're pushing a door, right? If you're pushing the door at its, the radius goes this way, you push the door this way. That's why you don't have to do a sign or anything like that. Thank you for that. Okay. So we're down here. We have the torque times the radius equals 1/2 mr squared. I'm going to rewrite this one more time. Okay. And I'm just using little r and big R interchangeably. I don't know why, I'm just doing it. So now let's solve. So we have 2 times 0.3 Newton meters over 2 kilograms times the radius, which is up here, 0.03 meters. Okay. And this gives us an acceleration of 10 meters per second squared. (10 meters per second squared). Yes?
Where did the radius squared?
Okay, so in this equation right here, I kind of just started solving on my own. I probably should have said something. So there's a 1/2 in the denominator. So I moved that to the top. That's where the 2 came from. Up here we have an r and then an r squared. So I just kind of canceled them out. Yeah, so I probably should. I kind of get ahead of myself sometimes. But yeah, this is a nice comprehensive problem for, especially for the people who have all this material as their final. It's a pretty good comprehensive problem for that. So are there any questions before I move on? All right. Yes.
How did you know, like, what were the key parts in the problem that told you you had to work with torque instead of, like, say, I don't know, like linear acceleration is equal to IW? Like, why did you choose the torque equation versus, like, I don't know,
Um, So I'm just going by what we're given.
Okay.
So, and that'll be a lot of it. So your professor won't really throw too many curveballs necessarily, especially I think for an introductory class like this. So I think a lot of them will be based on the equations you're given. That's why I really, really support writing everything out. I'm a big proponent on writing everything out. I'm a big proponent on crossing out units and stuff like that. It's just an easy way to, you get it all visualized and then you can attack from there. All right, so number 6. All right, now we have like the most classic Physics 1 problem ever. So block A, with a mass of 10 kilograms, rests on an incline of 30 degrees to the horizontal. So I'm going to draw that out real quick. And I'm sorry if this is crude drawing. So you've got an inclined plane, like here. That's 90 degrees. An incline of 30 degrees to the horizontal. So that's going to be 30 degrees. You have block A, which is 10 kilograms. So I'm going to draw a big block, call that A, on there. Now we have coefficients of kinetic and static friction are both 0.2. So I'm going to write these down. We have the mass of A is 10 kilograms. The attached string is parallel to the incline and passes over a massless frictionless pulley at the top. Of course, they always do that. So, we got the pulley right here. There's a string that attaches to that. Block B, with a mass of 7 kilograms, is attached to the dangling end of the string. So we're going to assume that it goes around this corner like this, and that's mass B. Is that drawing okay? Do I need to redraw it bigger? Okay. So block B, mass of 7 kilograms, attached to the dangling end. We're looking for the acceleration of B. Okay. So I'm also going to write down the mass of B, just so we have that on there. All right. So what are the forces that we have acting on this system? So
Gravity and tension.
we have gravity and tension, right? So we've got MBG going this way. We have tension going this way, tension going this way. I have a feeling those will cancel out, but we'll get to that later. We have, this is going to go vertically down, right? Because gravity always acts vertically. We're also going to have friction. So friction opposes the direction that you expect it to go. So because 10 kilograms is greater than 7 kilograms, what way do I expect this to go? I probably expect, because this is going directly down, that the overall system will go this way. So I'm going to say that friction acts this way. It opposes the direction that's expected. FF. Okay. So now we need to get this in terms of directions that we need to go. Okay? So we need to be following the direction of acceleration, which is basically along the line of this string. Everything needs to go in that general direction. So what we're going to do, I'm going to redraw this little area down here. So we have mass A. Mass A, 30 degrees. And that acts vertically. And that acts that way. Okay. So what we need to do is we need to break this up into x and y components. Now you're always going to have to do this. I guarantee you'll do this on your final exam. So what I'm going to do is I'm going to draw this again over here. That main force that you derive everything off of must be the hypotenuse. I used to mess this up all the time. I would always get this wrong on exams in Physics 1. And it's a really dumb mistake. Just remember, this will be the hypotenuse, this MAG. All right? So you've got this right here. Now, the forces, the lines that we're going to need, one going this way, we'll call that Fx. And then one going this way, that's Fy. This is getting kind of rough and crude, but that's all right. So when we draw this out this way, it'll be something like that. Okay? So the 90-degree angle will be here. That makes sense because we want MAG, the weight of A, to be our hypotenuse. That's the main force we're deriving these x and y components off of. So we're going to call this Fx, and we'll call this Fy. And that's because in our main drawing, because of the angle, I'm referring to this direction as x and that as y. So back down here. So the confusing part about this kind of stuff is what to do with the angle. Where is theta? So over here, we have 30 degrees. But it's kind of tough to just immediately visualize where that 30 degrees will be next. So I'm going to do my best to explain this now. Okay. So zooming function. All right. That's not how that works at all. Okay. So I'm going to redraw this one more time. All right. That's theta. This is the theta we know. Down here is mg. And this is some angle that we don't know. But we do know it. We know that this angle is 30 degrees, and we know this angle is 90 degrees. So all the angles in a triangle add up to 180 degrees. So we know that this is 60 degrees. Okay? So now if we're looking at this right here and putting that over here, so we have this line that goes down like this at 60 degrees. This line, the incline right here, and the normal force, that y component, will make a 90-degree angle. The normal force is always 90 degrees to the plane that the block is sitting on. So, because this is 60, we know this must be 30 degrees. Does anyone have any questions about how I just got there? This is like real prime, don't mess this up material. This is important. All right. So now we got that. So if we know this is MAG, we know Fy will be MAG times the cosine of 30 degrees. And I got that because of that. We all know SOHCAHTOA, right? All right, so if we have Fy is MAG cosine of 30 degrees, Fx is going to end up being MAG sine of 30 degrees. So now we have components for our forces, which is nice. That's good. We need forces. Okay? So why do we need forces? Because we're trying to find an overall acceleration of block B. But because there's a string and they're all tied together, they're one. The acceleration of A moving this way is the same as the acceleration of B moving this way. It's all one system. So we're going to do a nice sum of the forces equals the mass times acceleration. Okay? So what mass is really being considered? I just said because the strings are connected, like in the second problem we did, those strings are connected, right? So we've got basically this, and there's like a pulley, and then there's another. If block A moves at all, then block B moves with the same acceleration because they're tied together. So I'm going to rewrite this sum of the net forces. That mass is going to be the mass of the overall system. Will be mass A plus mass B. Times that net acceleration. Okay? And that'll be equal to a bunch of stuff. So, based on this drawing up here, and this is just my convention, you can think about it another way, it really doesn't matter. It's all about how you set up the problem. So, I'm considering anything positive is going to make this whole system go in that direction. It's going to make block B move down, and it's going to make block A move up. Okay? So what makes block B move down? That's MB times G. That's positive. And that's really the only positive thing we have going on. Everything else is the only other real two forces we have that are impacting this is friction, which is opposing that movement, and the gravity of block A making the block slide down. Okay, so the rest are going to be negative. So MBG minus, let's do the mass of the block. So over here, we just determined a way to calculate the mass of the block sliding down, right? That's what this is. That's the component of gravity that's making block A slide down the block. So minus MAG sine of 30. And then I'm going to do minus friction. What's the equation for friction? We have mu k times the normal force. The normal force, as I said before, acts perpendicular to, I'll point up here, I guess, acts perpendicular to the plane. And we found that right here with m times cosine 30. Yeah, I'm sorry. And now we've got a nice big equation. With everything is known, except for the thing we want, which is that acceleration. So do you guys want me to write out all the math, or do you want me to just stop here and move on to the next? I mean, I'll give the answer, I guess. So this is a really good, comprehensive overall problem. This is totally going to be on the test. This is totally an awesome problem. And it's probably my favorite kind of problem to do in physics. So are there any questions on how I got this overall equation? Are there any questions about how I found the x and y components of the block on the plane? Because that's like real important. Yes?
So the reason our tensions are in the summation is because they cancel out, right?
Sorry, what was that?
Why aren't the tensions in the summation of forces? Do they just
So I could have put them in there, but they would have canceled out. Yeah. Because it would have just been I guess, this one would have been plus t, this one would have been minus t. A lot of the time with the Pulley problems, that unless they ask you for tension, a lot of the times they're just going to cancel out. Any other questions? Okay. Next question. So I might have to, I'm not sure if I have to speed up or not. I think I'm doing okay on time. All right. So we have a block of a mass 2 kilograms that's stationary on a horizontal table. The coefficient of static friction between the block and the table is 0.7. What is the friction force? All right, so let's draw this out. We got a block right here. That's 2 kilograms. We know that coefficient of static friction is 0.7, which is pretty high. However, they say the block is stationary. If the block's stationary, it's not moving. Nothing's really happening. So what forces are really acting here? We have the gravity of the block, mg, and then we have a normal force pushing up from the table, I guess. Normal force Fn. Okay? So this is all we have going on. So I guess the way to proceed would be sum the forces in the x, sum the forces in the y. Which is a pretty good go-to if you don't know what to do. So sum of the forces in the x are going to equal the mass times the acceleration in the x. So what forces would act in the x direction? The only force would be friction, right? Let's just say friction acts that way. I forgot to include that one. But there's a problem here, and that's that the block isn't moving in the x. There is no acceleration in the x. There's no acceleration in the y. Both accelerations are 0. So the acceleration in the x is 0. And that means the force of friction is also 0. Does everyone see how I got that? Okay. I actually had a really I remember I had a similar problem on my final exam, and I got it wrong because I didn't know what to do. Because it seemed too easy. But that's it.
just because it's not moving, that's it?
Yeah. Yeah, exactly. That's kind of like makes the life easy. Like in the last problem, we assumed the whole system was moving, and we were finding an acceleration. Because it's stationary, acceleration is 0.
Right, you would think like this would be like mu times the natural.
Exactly. So they were just trying to trick you with a bunch of knowns. All right. So we're going to go to a little bit more of a kind of a more advanced problem. And I'm going to do my best to fit this all on one paper. Should be fine. Okay. So we have a uniform ladder of length 2 meters that is leaning against a window, and it makes an angle of 30 degrees to the vertical. All right. So bear with me. Draw this out. We have the ladder goes up like that, right? All right, that's the ladder. We know has a length of 2 meters, and it makes an angle of 30 degrees to the vertical. That's a key word, to the vertical. So this is what's going to be 30 degrees. Okay, to the vertical. There was no friction between the ladder and the window. Bless you. The coefficient of static friction between the ladder and the ground is 0.6. So I'm going to kind of rough this up a little bit, and I'll call mu s to be 0.6. The window, which is going to be up here, something like that. The window can withstand a force of 10 newtons without breaking. So I'm going to call F max to be 10 newtons. What is the maximum mass that the ladder can be? So I'm going to call that ML. We don't know. And that's what we're looking for. So number one, the way that you always start this is going to be summing the forces in the x, summing the forces in the y. But first, let's break down what's going on at this window. What's happening at this window? What's happening with the forces all over? So I'm going to start with the ladder. Obvious with the ladder is mass times gravity, right? So that mass times gravity is going to occur at the middle of the middle of the ladder. In later classes, they'll tell you that that's not right, but like for now, that's how we do this. So that force is ml times g. What else do we have? We have, it's kind of tough to draw. So we've got a force going like, some force that's kind of pushing into the window, and that is that F max. That is 10 newtons. So that arrow, that's kind of an arrow, and that's pointing to the window somewhat. Okay. So do you guys think this will be a force problem? How do you think we're going to approach this? So it's kind of a tricky question. Because it's not going to be force, it's going to be torque. And that's because the ladder is going to rotate. That's how it makes its impact. That's how it moves. If this was like a horizontal ladder or something that just went like that, that would be force. But because it's kind of here and it leans on that window in a rotational motion, it's got to be a torque. So the way I'd like to think about this is that the torque from the window will have to equal the torque from the ladder. Okay? And torque, we know, is F times R. And you can do a sum of the torques. It depends on how you want to do it. That equals 0. So one more thing we need to do is we need to break this ladder up into x and y components. So we've got this ladder that kind of goes like that. I really need to make my drawings bigger. So we got a ladder that goes like that. mg, the weight, occurs at the middle of the ladder, so at a distance of 1 meter, right? And that acts down at an mg. And this is just like the last problem, or 2 problems ago, whenever that was, where we need to get this broken up into x and y components, where this is the hypotenuse. So I'm going to draw this with these dotted lines. Okay. So I'm just going to redraw this. All right. Something like this, okay? And we know this is mg. Up here on this main picture, we have this is 30 degrees. We can call this 60 degrees, just based on them equaling 180. So that means down here, this angle is 60 degrees. We know this angle right here is 90 because mg is the hypotenuse. And it depends how you want to do it, but I like to do it this way. So this right here makes its own 90-degree triangle. That blue that doesn't show up blue at all makes its own 90-degree angle. So that's right here. And we know this is 60 degrees. So then this is 30 degrees. Okay? And then it's just like that last problem where now this overall is going to make 90 degrees. So that angle right there is 60 degrees. Okay? So then I'm going to translate that down to here, 60 degrees. That's supposed to be a right triangle. That's pretty bad drawing. So then using SOHCAHTOA, and this being 60 degrees, we know this will be mg times the cosine of 60 degrees. And this will be mg times the sine of 60 degrees. So that gives us a way to break it up into x and y components. All right. So at this point, I'm going to kind of redraw the window, because that's where the action's happening, right? So this is our window. What's happening at the window? The maximum force that it can withstand, so I'm going to pretend that it's pushing from this way, that the window's pushing back. That Fw is 10 newtons. Okay. What else do we have? We have the force of the ladder. So that ladder from up here is kind of leaning down on that window. So I'm just going to point in some generic direction, and that's the force of the ladder. So these are the main things acting on this window. These are the two things that are making a torque on this window. All right. Okay. So I'm going to redraw. Okay. A lot of redrawing. So this force of the ladder, right, that is pushing downward at a certain angle. What angle is that pushing at? Okay. So that's why I'll draw it up. So we've got, this is 30 degrees. This is going to push down also at 30 degrees. Because it made a 30-degree angle with the vertical from up here. So this going downward will be at 30 degrees. Okay? And that's going to be important for right here. So that's going down at a 30-degree angle. So let's move back up here and set the torques equal to each other. So the torque from the window. We know a torque has to be a force times a distance, right? So the torque from the window is going to be 10 newtons times the cosine of 30 degrees. And that is from 2 meters of ladder length. And that's equal to torque of the ladder. So the ladder, that FL, we have over here. Okay? And that's because that force acts down there. We translated that over. That force is acting up there. That might be a little easier to recognize. So that's the force of the ladder right there. And that's acting down at that 30 degrees. So, that will be mLg times the cosine of 60. And the force of the ladder that's purely based on the weight. So what we were saying before, that weight occurs at the midway point of the ladder. Because we know that the ladder is 2 meters long total, the midway point of that ladder is going to be 1 meter. So this is our equation with all knowns, and the only thing we don't know is what we're looking for, the mass of the ladder. So when you solve that out, that comes out to 3.4 kilograms. Does anyone have any questions? That was a pretty confusing problem, so I kind of understand if you do. Yes?
Why is the force that the ladder is exerting on the window 30 degrees?
So, okay.
Because it's different than the one it exerts from the wall, right? Like then the angle between the ladder and the wall, that's different than the force.
So the force of the ladder, that's from the weight of the ladder. Okay? So, so that's kind of down here. Okay? Sorry, I think I mixed up. I think I mixed up an FL and an FW at some point.
Would it have to equal 90? Is that
What do you mean by that?
like the 30 degrees and then the angle that the ladder makes on the window, like the force?
Yeah, so it's kind of based on this down here. So the ladder is, this angle right here is 60 degrees. This angle right here is going to be 30 degrees, right? So when you do, you have that, that is going to be the force that you act on the window with, right? So that will be a total of 90 degrees. And then that, it's kind of confusing. This up here will be 30 degrees.
Wait, can you, it's a bit hard to see, it's a bit bright.
I don't.
Moving it down maybe? Yeah, that works a little bit.
Yeah, it's kind of a tough, the pens aren't really the best for this. Yeah,
It's a little bit
sorry.
confusing, but
Yeah, I know. I didn't really answer your question too well, but it's kind of hard to verbalize. Are there any other questions? Yeah.
Can you explain again how you got 1 meter, or like explain that?
Yeah. So the torque from the ladder is based on the weight of the ladder. That's really the only thing that's impacting it. So we assume in Physics 1 that the weight of something occurs at its center of mass, its center point. And for this ladder, that's going to be at the middle of the ladder because it's a uniform ladder. Yeah, they actually say it's a uniform ladder. So because the ladder was 2 meters long, that center of mass is at 1 meters from that point that everything is acting at. So in this right here, this whole length was 2 meters. It only acts at this middle point, so then the distance from here to here is 1 meter. Does that make sense? Yeah.
So when we're analyzing it from the torque produced by the ladder, we take the 1 meter because of the weight, but we use the 2 meters and the torque from the window because it's like the full hinge of the ladder.
Exactly, because it's the full hinge of the ladder. Yeah. Any more questions? I don't know, I'm not doing the greatest on time, so I'm sorry if I don't get to everything, but I think I can. All right. So number 9, we have a particular spring that doesn't obey Hooke's law. What is Hooke's law, just for quick review? F equals kx. Kx, negative kx, depends on how you want to write it. Cool, that's Hooke's law, just for fun. But in this case, the spring doesn't follow it. So the force of the spring is given by this equation. it didn't really come out. That's 60x squared. It's supposed to look like that. So when the spring is compressed by 0.1 meters, so let's call delta x to be 0.1 meters from its equilibrium, how much energy is stored? Okay. So an important thing for Physics 1 for engineers, that's what differentiates it from college physics, is knowing the integrals and the derivatives and all that. So one of the main things that you guys should have gleaned is that the energy is the integral of the force. So normally, let's pretend this is a normal spring. We know F is kx, right, for a spring. When you want energy, that's going to be the integral of force. And then from power rule in Calc 1, that's 1/2 kx squared. So normally, the potential energy in a spring is 1/2 kx squared. But in this case, we don't have kx. Instead, for some reason, our force is represented by that equation. But we're going to follow the problem the same way. So,
Good question.
yes.
Isn't work usually the integral of force?
Well, work is the change in, it's kind of related. It's kind of the same thing. So work is,
Isn't
The-
there's an equation that's like work is equal to the integral of force times distance, or the integral
well, work is force times distance. So the way you could think about it is that work is the change in energy, kinetic energy. So when you move something, that's kinetic. So a force times a distance, you could think of work as like the integral of force from x2 to x1, where that distance is x2 minus x1. So it's the same thing.
is that so? That's what you're just doing right now, or
Yeah, so in this problem, instead of having the force equals kx, the force is represented by some other equation. And that could have been from some computational fluid mechanics, I really have no idea. But they got this equation for the force. And they want to know how much potential energy is in this spring. So we're going to follow this, basically the same rule. So energy is going to be the integral of f of x, which is the integral of this equation. All right, and that gives E of x. So we're doing like the reverse power rule. I don't know what the word is. So this should be negative 10x squared minus x to the third, so that'd be 20. And I believe we just ignore the plus c thing for now. So this is our new equation for the energy of this spring, this made-up energy, okay? What they wanted to know, when the spring is compressed by 0.1 meters, how much energy is stored? So, from this equation right here, all we need to do is plug in 0.1. And when you solve that out, that'll come out to 0.12 joules. Any questions on this? Anything from here? Yeah.
If it were stretched instead of compressed, would it still be 0.1? Does it matter with size or something?
Good question. I don't think it should matter for a spring. I think it'll be the same nonetheless. Because if you were to compress it, it's going to shoot out the same way as if you pull it, and then let it do its thing. That's kind of the interesting part about a spring, that it contains its own cyclical force either way you pull it. So yeah, it should be the same answer nonetheless. All right, so I'm going to go to number 10. Which of the following is not an example of a vector? So you have displacement, temperature, velocity, and acceleration. Anyone know the answer? You guys should know this. B, temperature. So I'm going to use this time to go over normal vector things because it's like a weird subject that students have a lot of trouble with. So normal vectors are these three. So you could have v equals vxi plus vyj plus vzk, right? Everyone hates this vector notation. So two important things that you guys need to know are the dot product and the cross product. So let's pretend you have two vectors, a dot b. I think someone was mentioning it before. So the dot product is going to be the magnitude of a times the magnitude of b times the cosine of the angle between them. Okay?
But sometimes it's sine, isn't it? Or-
That's the cross product, which I'll write right now. Yeah, no, you're good.
There we go.
Yeah. So a way you can calculate this is going to be so this one's kind of, this is much easier to calculate than the cross product, which I'll go over in a, did you guys have to calculate the cross product if you were given like vectors of 3 components?
Maybe like chapter 1.
You didn't have problems where you had to make like the little matrix and you go down the lines and stuff? Cool, I won't go, you did that. Okay. Yeah, but you were given something like, you were given something like that and then said find A cross B? Okay. And you're in Physics 1 honors, normal? Okay. So I'm gonna go over it then. So let's pretend these are the vectors for this one. Dot product is real easy. You take the two x components and multiply them together. So you do 3 times 6. So you get like 18i. The two y components multiplied together. So 4 times 3, that'd be 12j. And then you'd have the two z products, so -6 times -1, that'd be 6k. So that's what the dot product is. You can also find them two magnitudes and then multiply them. Then that's how you can find the angle between them. So I can easily see you guys having a problem related to something with angles between, like find theta based on given these two. That's a pretty standard problem to receive. Then the cross product is A cross B. And that, like you were saying before, is magnitude of A times the magnitude of B times the sine of theta. And then I'm just going to go over it real lightly because it's kind of a whole production. But if you wanted to calculate, if you were given these A and B vectors before, and you just wanted to calculate the cross product of them, so the way to write it out, you do I, J, K. And then you would put your AX AY, AZ, BX, BY, BZ. And then you're basically going to go in diagonals and subtract. Okay, so I'm just going to have to write this out. So for I, you're going to go down this diagonal. AY times BZ plus J, you're going to go diagonal, so AZ times BX plus, for K, you just kind of move over to here, so AX BY. And then you're going to subtract going the opposite direction. So here you have I, so you're going to kind of go to the other side, AZ times BY. I plus J, you go the opposite way, AX times BZ. And then K, you'll go this way, AY, BX, K. And then you could get just an overall vector from there. And then you could use that to plug back into here if you ever needed to solve for that theta. So it's a lot of boring stuff, but it's kind of useful, actually, eventually. Yes?
So fundamentally, what's going on in the cross product is like we're multiplying every single term, but within every term, like a subtle right-hand rule is applied, right? And that's why we get this formula, because some of them cancel.
You kind of lost me on the right-hand rule part.
Because as we have our, like with the first term with our AY, BZ, as we go from there, we can see it's going to be a vector in the direction of I, or a component of I.
This is just like a computational way to find, like, if you're given, kind of like how we were up here with these A and B, if you're given two vectors, that's just a computational way.
I don't know if like that was the definition or if that was the fundamentals. So.
Yeah, I mean, this is, you could memorize this equation if you wanted, but this is just an easy way to, because I wouldn't want to memorize that. So it's just an easy way to get that.
Okay, cool.
Yeah, this isn't really like the fundamentals of cross product, which I think is kind of above this class anyway. But I think you only use that in, yeah, torque is force cross R. So you could have a problem with that, but I kind of don't foresee that. I think if you got a cross product problem, it would be more basic like this, I would think. Yeah, no problem. So that's vector stuff. I wouldn't be shocked if that was on the test. So, some rule states that while one form of energy may be transformed into another, within an isolated system, the total energy remains the same. What's the answer? Anyone know the answer? The answer is B. Conservation of energy. Now, most of the time, and probably for this test, energy will be conserved because you don't really have time to start solving these crazy problems. But there's two main things that can happen to cause to cause energy to not be conserved. And that is either energy is lost in the system or something acts outside of the system to add energy to it. So the most common one that I would imagine that you guys would get is friction. So in that problem before, when we had the two blocks sliding on the thing, friction was causing that energy to not be conserved. Another one would just be work done by an outside force. And that could be, I've got the two blocks on the pulley, but then I pull one of the blocks with a 10 Newton force. If I did that, the energy wouldn't be conserved anymore. So, but again, I would expect most of the problems to conserve energy, but just keep these in mind. It's just good to know. All right, next question. Okay, so we have a tank of water that's mounted on wheels and rolls without frictional losses on a track. So no friction. As the tank moves, water trickles out at a constant rate through a hole at the bottom. The speed of the tank will ... So let's draw this out just to clear up what's going on. So we've got some type of truck like this. It's moving at an initial velocity. And then at some point, water is trickling out, like here or something. So now it's over here with a new velocity. So the question is basically asking, how does VF compare to VI? So what's everyone's initial thought on this? So you think if water was spilling out of the tank, then the speed would decrease? I don't know who said that. So it's losing energy, so you expect the tank to slow down. Okay.
But as it becomes lighter, then one will move faster?
Yeah, so that's more on the right lines. So because the truck is becoming lighter because it's losing water, then it's going to start going faster because we assume that it's still, energy isn't really being lost. If anything, energy isn't really being lost, it's just mass that's being lost. So we could think of it in a way of like conservation of momentum, right? So m1v1 equals m2v2. So you've had like the classic problem of like two balls hit each other and bounce off in different directions, or they stick together, or whatever. That's based on conservation of momentum. So this is kind of conservation of momentum, but it's not really too. So if you were to increase that final velocity, right, as we're talking about, kinetic energy is 1/2 mv squared, right? If the velocity is less than it is in the beginning, then we kind of lost an energy, right? We've lost kinetic energy. But if there's conservation of energy, then it's just stored in more potential energy. But that's not really happening in this problem. There's no potential energy. There's not like a ball rolling up a hill. There's none of that. So if anything, we can't really count that either. So basically, instead of just the mass of the truck and then the mass of the truck later with different velocities, we kind of have to break this up into, number one is going to be the mass of the tank plus water times the initial velocity. And I know these are kind of ridiculous, but just to write it out. That's going to equal the mass of the water times the velocity of the water plus the mass of the tank times the velocity of the tank by itself. So if this is going downward and the tank is still going forward, then it still holds that the velocity of the tank at the end will be greater than that in the beginning. So the initial thought process was right. So it kind of makes sense. All you need to do is think about it in a logical, normal way. The truck, it's not really losing energy. It's kind of staying the same. It's just losing mass. So to make this equation right here work, if this mass decreases, then this velocity must increase to keep them the same. So the answer is C. Increases at a constant rate. Okay. So now we're going to move to kind of an angular problem. So we have a 15-gram paper clip that's attached to the rim of a record player rotating at some speed that I don't really care about right now. So I'm going to draw this out. We've got a big circle. Pretend that's a circle. It's on a record player, so there's that inner thing. So a paperclip is attached to the rim of the record player, so I'm going to just draw like a shaded in square or something. So that's the paperclip. We know the mass is 15 grams. And it's rotating like that. And it's rotating, thank you, at 3.49 meters per radians per second. Okay. The radius of the record is 15 centimeters. So we know that that distance is 15 centimeters, which is 0.15 meters. What is the angular momentum of the paperclip? So I've seen this written, the variable is L. I don't know if you guys have a different variable, but this is what I call angular momentum. That's what I've always seen it as. Okay. So there's an equation that you guys should be provided with on your formula sheets. The angular momentum is equal to the mass times the velocity times r. Have you guys seen this equation before, or is this like kind of some brand new thing? Okay, so this is normal. Everyone knows this one. So we need L, and we have M, and we have R. So this is good, but we have a V here, and we don't have any V normally. But I was showing a few problems ago how you can relate linear to angular, okay? So I think I learned these back in like 8th grade or something. So there was like S equals R theta, and then we have V equals R omega, which is the one we want. We know omega, that was given in the problem. And then we know R, and that was also given in the problem. So now we have something for V. So I'm going to rewrite that equation up here as L equals M times R omega times R. Because there's two R's, I'm just going to write this as M R squared omega. So now we can find our angular acceleration in terms of all stuff we know. So L is going to be equal to the mass, which is 15 grams. So I'm going to need to actually convert this to kilograms. Because remember, kilograms is the SI unit. So we have 0.015 kilograms times the radius, which is 0.15 meters squared, times that angular acceleration that was given, or angular velocity rather, 3.49 radians per second. Okay. And now at this point, just multiply it out. And that'll give us and the units check out as well. Kilograms, meters squared, radians we can ignore per second. Does anyone have any questions on how I got this answer, how I came up with it? Okay. A lot of this stuff is just going to be playing around with the formulas you're given and turning it into something you know. Okay. So in this problem, we have a 1,000 Newton sine. So it's just a fancy way of saying that it weighs how much it weighs. It's suspended from the end of a 4-meter boom attached to the wall by a hinge. One end of the supporting cable is attached to the end of the boom, while the other end of the cable is attached to the wall 3 meters above the hinge. So you can see here, that distance right there is 3 meters. And the boom is 4 meters long. The boom is uniformly constructed and weighs 400 newtons. What is the tension in the cable? So there's a lot of stuff going on. What do we know? So we know that the sine weighs 1,000 newtons, and that acts on the very end of this boom. We know that the boom itself, it's uniformly constructed, and it weighs 400 newtons. So this is kind of like that ladder problem. So because it's uniformly constructed, we assume that all that weight is going to occur at the center of the boom. So somewhere right there, with that distance being 2 meters. And that force downward, that weight, is 400 newtons. What else are we missing? So what other forces do we have in here? We have the weight of the boom, the weight of the sine, and then the whole thing that's kind of holding this thing together, which is the tension in the cable, T. So overall, we have, this is going to be a torque problem. And that's because we have things rotate, we have a beam rotating and forces preventing it from rotating at the same time. So we're going to consider this point right here to be our axis of origin. I feel like I'm missing something. Yeah, okay. So we have the sum of the torques in this problem are going to be 0. Why is that? That is because this isn't moving. If this was a whole moving system, then the torques might equal something, if a torque was given or whatever. But because this sine is being held by a boom, you don't want it to be moving. That's the whole point of engineering this thing. So we know that the sum of the torques is going to be equal to 0. So what are the sum of the torques? Personally, I've always had the convention of counterclockwise is positive, which I think is pretty standard. So I'm going to consider anything that makes the boom go in this counterclockwise direction to be positive. So what's making it go in that direction? Only the tension. So we can't really use this tension. We want the tension that goes like this. We want that y component of tension because that's what's acting in the that's what's acting perpendicular to that overall motion. It's like the door. So if we're going to draw a nice little triangle like that, we have this is our right angle, and then we want opposite of that should be our tension, which is true in this case. So Ty, oh, we don't have a theta, but we can find a theta. Okay, so I'm going to redraw it like this. We've got 3 meters, 4 meters, and this is a right angle. So I just remember from a long time ago the 3, 4, 5 triangle. It's like an ultimate classic. But if you guys didn't know this, you could have just found, you could have done some form of SOHCAHTOA and gotten an angle. But I've memorized that. I don't know if you guys have memorized that as well, but that's just a rule. So we have that. So the y component up here is going to be basically 3/5. So sine of theta is opposite over hypotenuse. So, or you could just look at this right here. That's the 3 meter. That's the 4 meter. That's the 5 meter. So that value is just going to end up being this length over this length, which is 3/5. So 0 is going to be T times 3 over 5 minus things that make this go the opposite way. Okay? So we have, let's start with this thing, the force of this sign. So we know that the sign weighs 1,000 newtons. They could have also given us the mass and just multiplied by g, same thing. And this occurs at a distance of 4 meters from the hinge point. So that right there is going to be 4 meters. The other thing that's making it go downward is the weight of the boom itself. So we know that the boom weighs 400 newtons, and that occurs at that halfway point because it's uniformly constructed. So that distance will be 2 meters. So now we have all these known things, and we can solve for RT. And when you do all the math, that tension in the cable is going to be 8,000 newtons. So let's sit back for a second and fact check that and see if that makes sense. So our total forces acting downward there's that 1,000 Newton force and that 400 Newton force. That tension is the only thing resisting that motion, and it's going at an angle, like a pretty steep angle as well. It's not like the best angle on Earth. So that tension is going to have to be really high to make up so that this whole system doesn't move. So the answer makes relative sense. It should be about, it should be significantly more than the total of these two forces. So that's something I like to do at the end of problems, is to make sure that it kind of generally makes sense. So are there any questions on how this problem was done?
Just like to put it in real terms, like 8,000 newtons. So like the cable has to hold 8,000 newtons, or like?
That is the force with which the tension is pulling.
Okay, so it has
So
to be
it's
able to withstand 8,000 newtons.
Yeah. So if you were like buying the wire or whatever, you would need to make sure that it can withstand 8,000 newtons of force. Yeah. So that's realistically like the engineering part of where that would come in. All right. So I'm going to move on to number 15. Oh, nice and quick. Blank is a measure of how quickly work is done or how quickly energy is sent or gained. So what this question is asking is how fast work was done. So you could also think of it as the change in work over the change in time. What do you guys think the answer is? Any guesses? Okay. Did you guys learn about power? No? Is this a waste of a problem? No one learned about power? We did power? Okay. So I'm going to go over what power is. So you think of power, and you think of you kind of think of like how much force is generated, but it's not necessarily that. It's a force times a velocity. So really powerful people are people who have a lot of force and do it quickly. So it's a force times a velocity. And this kind of makes sense. So we talked about force before, right? And we were saying that work is the integral of force. We said that before. And then you could rewrite that as the force is the change in work over the distance. So let's put that in here. So force is dw over dx. And we know the velocity is the change in distance over the change in time. And look at that. They cross out. Power is the change in work over the change in time. That's kind of exactly what the question was asking, too. How quickly work is done. So, math. Yeah. Math is cool sometimes. So, any questions? Okay. So blank is the quantitative measure of the tendency of a force to cause a change or rotation, what am I doing? To cause or change rotational motion around a certain axis. Torque, yeah. We just did like a bunch of problems about it. Torque. You got the little beam like that. Torque goes this way because of a force pushing like that, and a radius r. So it's like the classic door example is like my favorite torque example, force times the distance. All right. How much work is done by a 55 Newton force pulling a suitcase at an angle of 75 degrees from the horizontal for a distance of 27.5 meters? It's a lot of stuff, so let's just draw it out. So that's my suitcase. So a 55 Newton force pulling at an angle of 75 degrees from the horizontal. So that means, let's just pretend we've got a force like that. F equals 55 newtons. And it's 75 degrees from the horizontal. So that angle is 75 degrees. It moves from here, and it's going to go all the way over here. And that distance is 27.5 meters. So you're pulling it pretty far. Okay. So what is work? And this is a pretty simple problem. So in this one, you can just think of it in normal terms. Work is a force times a distance. But work can also be, what's the term? In x and y components. So you are moving this in the x direction. You're moving it 27.5 meters in the x. So that force that you're pulling with also needs to be in the x. So we need to break this 55 newtons up into x and y components. So I'm going to move down here. We know that's 55 newtons. And it makes this angle of 75 degrees. And that is going to be 90 degrees because the 55 newtons is your hypotenuse. Always remember. And that will give us an Fx and an Fy. And then good old SOHCAHTOA tells us that Fx will equal 55 times the cosine of 75 degrees. Does everyone see how I got to that point? Okay. So now we have Fx. We can plug that in to our work. So work equals 55 times the cosine of 75 degrees times the distance that it moves, which is 27.5 meters. And we calculate it out. That work is 390 newtons. So it's a pretty simple problem. It's reasonable that that would be on the test. I think your test will probably be a lot of like small ones like this and then a few big problems. So it's good to have. Any questions? All right. So this is the end of all my questions and all that. Just some last minute tips, and they're all basically the same tip. Practice problems is number one. Just do practice problems, get them in the book, get Chegg. I know I'm not supposed to like say you should get Chegg, I'm doing it on camera. Get Chegg, it's like the best resource you can have, not to do for your homework, but so that you can have unlimited practice problems. Because you could have the answer in the back of the book, but you like if you don't know how to do the problem, you're not really helping yourself. So I'd recommend getting Chegg. Redo old exams and quizzes, because professors like to repeat their stuff, because they're lazy, just like me. Practice problems and practice problems. And that's what I recommend. Yes?